Welcome to lecture 22 of Power System Protection course. In the last lecture, that is lecture 21, we discussed a illustrative problem regarding the how we can design a differential protection scheme for a transformer. We have designed that, we have discussed that. And also again we studied regarding the high resistance fault. When there is a high resistance fault between the winding to core, in fact because the core is laminated and the current path through the core will be resistive, highly resistive, so therefore it is called high resistance fault. And when such high resistance fault occurs, in fact it is very difficult to detect this kind of fault through the differential protection scheme or overcurrent protection scheme. So therefore a special arrangement is made for this kind of fault. Now we can see this in detail. Already we have discussed this, again we can just revise this. So this is called, also this protection scheme is known as the restricted earth fault protection scheme, and this kind of fault is known as the high resistance ground faults, right? And the protection scheme known as restricted earth fault protection. So already we discussed this, that when we will consider a delta star transformer, in that case, if we are going to provide this protection, this restricted earth fault protection to delta side, then we need to make such arrangement, like we will put a highly sensitive overcurrent relay just by connecting the cities in star fashion and connecting finally to the overcurrent relay. And whenever there is a fault, winding to core fault, so under that condition only this kind of relay will sense the fault current. Unless that, under any other condition like a normal loading condition, or if the fault is happening somewhere here in the star side, even if that is the highly resistive ground fault, that will not be detected by this restricted earth fault relay. Similarly, this kind of arrangement can be made for the star side, like we can see here, right? So for star side also this kind of arrangement can be made, and also it will respond only the fault when it is happening, the winding to core fault at the star side, not for normal loading condition or any fault at the delta side, it will not respond, right? Already in detail we have discussed in the last class, so no need to discuss more. You can revise that. Now we will see in this lecture some of the incipient faults and also interturn faults, which are very important in fact, because it does not reflect much to the differential relay or to the overcurrent relay, but somehow it gradually accumulated by the aging effect, gradually it becomes a very severe fault. It in fact creates severe fault condition if it remains for more duration. So this is your interturn fault. Interturn fault means your fault is happening between two turns, right? So here we can see this is one turn and this is one turn. Let us say somehow if the insulation between these two turns breaks down and these are shorted together between these two turns, then obviously if we'll see the voltage across this fault, voltage across these two turns will be very less. It may be around 5 volt. If we'll consider a transformer of 400 kV is to 11 kV, right? It is star transformer. If we'll consider, then it is a star transformer, and it's this 400 by 11 kV transformer, the voltage ratings. So these are line voltages, therefore the phase voltage will be 400 by root 3, here also 11 by root 3 kV, and therefore the voltage between these two turns will be 5 volt. And if we will see the fault resistance, it will be around 1 milliohm. So therefore your fault current, the value of the fault current will be very high. It will be around 5000 ampere, which is very high in fact. And because of this, some heat will be produced because of the I square R loss, and that heat in fact causes the hotspot, local hotspot. Let us see how it produces the heat. So if we will calculate the power dissipation in the faulty turns in the winding, then obviously it will be IF square RF, and your IF is 5000 ampere. If we will substitute the values, it will be 5000 square into 1 into 10 to the power minus 3, it will be around 25 kilowatt. So 25 kilowatt is in fact very high value, and which produces lot of heat, okay, lot of heat. So because of this, in fact your the windings become very heated up, and again it deteriorates the insulation of the winding, and it causes further faults in the windings, right? So now let us see what will be the impact of this current, this fault current, which is around 5000 ampere between these two turns in the primary side, whether this is amount which can be detected by the differential relay or the overcurrent relay, which is a backup relay. Is it possible? Let us see. So let us calculate the reflection of this current. In order to find that, let us say the load current is 0 here, and hence we can find the exact reflection of this secondary fault current in the primary side. So if we will find that just by putting V1 I1 equal to V2 I2, now I can say 400 by root 3 kV I1 equal to 5 volt here in the interturn, voltage across the interturns, into 5000 amperes. So I will get a current of I1 which is reflected in the primary side, that is around 0.11 ampere. The magnitude of this current is very less as compared to the magnitude of normal load condition or any external fault condition. So therefore it is difficult to detect this current with your differential relay or your overcurrent backup relay. So the current that circulates within the short circuited turns is 5000 ampere, whereas at the 400 kV terminals the current is only of the order of 0.11 ampere. Thus the interturn faults are difficult to detect using overcurrent or differential principles of relaying. However, they can cause severe hotspots. So that is the problem we will face. Severe hotspot it will create, resulting in deterioration of the insulation further. So now this has led to the development of Buchholz relay. So how we can detect this kind of relay? So this kind of relay can be detected by the Buchholz relay, which makes use of the heat generated and the consequent decomposition of the oil to sense the fault by purely non-electrical means. It is a non-electrical fault detection scheme. It in fact very useful for other incipient faults, like it also detects when the oil leakage happens and the oil level decreases. It also detects, and also it detects other hotspot phenomena in the other elements, like in the joints of the core, in the nuts and bolts of the transformer, right? So that kind of hotspot also, when it is heated off and it produces gas inside the oil, so the oil in fact expands by that way. So that way the Buchholz relay function. Let us see the Buchholz relay, the functioning of the Buchholz relay, how it is important. So Buchholz relay incipient faults in the transformers, how it in fact detects the incipient fault. What is incipient faults? So this is also a kind of incipient fault, we can say this Interturn fault, and there are other incipient faults like oil leakage and hotspot in the cores, right? So faults which are not significant, these faults are not very significant in the beginning, but which slowly develop into serious faults are known as incipient faults. Okay, so Buchholz relay provides protection against such incipient faults. How it provides? Let us see first the transformer, different parts of a transformer, how it is in fact it looks. So this is your casing of the transformer. This outside covering is the casing of the transformer, which in fact protects the winding and core from external effects like from sun, from heat, and from rain, right? And inside that we have oil. So this is called oil immersed transformer, right? These are oils, and so these are oil, it is marked, and this is in fact which is a gray color, it is in fact the transformer, right? So which in fact consisting of the core and the windings of the transformer. So this is your tank, this is outside covering is your tank, which in fact covers the main transformer, or the core and the winding and the oil. The core and winding are immersed in the oil, insulating oil, and these are the bushings we can see here. These are the high voltage bushings. Therefore more insulations there provided, and on the other side it is the low voltage bushings with less insulation, right? So now we can see these parts. In the left hand side we can see this is your conservator. Conservator is like a cylindrical structure, sometimes it is also made up of in the rectangular structure. So in some transformer you will find it is huge cylindrical structure on the transformer, right? And it is connected through a pipe, connected through a pipe to the main transformer, right? And why it is called conservator? In fact, it conserves the oil, and this oil is used when there is leakage of oil, and also when there is some gas is formed in the tank, the excess oil flows into the conservator, right? So this is the function of the conservator, right? So therefore it is a huge cylinder on the transformer. Okay, and another component is your breather. What is this breather? In fact, if we'll in fact see the transformer, this is in fact connected to the conservator. As the name suggests, in fact through this the transformer breathes. Breathes means it exhales the extra air when it is extra gas is produced, and when the oil level decreases it inhales the air inside, right? Okay, this is the breather. So In fact, this breather plays very important role, because this breather, in fact, through the breather it sucks air which is moisture free and which is free from all contamination, all pollutant. So how it is possible? There are two components in the breather. One is your filter, which in fact filters the impure elements in the air, like dust particles and other mixed gases, right? And another component is, one component is oil filter, okay, which in fact filters the air from all the contaminations like dust and other pollutant gases. And other component is your silica gel, okay. Silica gel in fact plays very important role to filter out the moisture, or to dry out the moisture in the air, which air will go inside. It will in fact, it should be free from the moisture. It is very important, right? So therefore silica gel, the role of silica gel is to dry off the moisture content from air when air is being sucked by the transformer, okay. So this is the structure of the transformer, what we are saying. And now let us see the Buchholz relay. You can see the location of the Buchholz relay here, right? The location of Buchholz relay is in such a way that it is between the conservator and the main tank, and it is installed in the pipe which is connecting conservator and the main tank, okay. So now we have four wires are coming out, two wires for alarm and other two is for trip command, right? So let us see how it functions and inside structure of the Buchholz relay, right? So now you can see here there are two contacts. It is going to alarm. When this alarm will in fact buzz, when this contact will be connected to this contact, right? That means when this will be sorted with this terminal. So how it is possible to be sorted? You can see this is the floating element, floating ball, right? Let us say floating ball is there, and when there will be leakage of the oil in the transformer, what happens? This in fact this ball goes down, right? When it goes, these are the fixed elements, fixed contacts, and when the ball comes down, this will go up, and as this terminal will go up and it will sort the two terminals of the alarm circuit and alarm will buzz. That means it is the alarm for the oil leakage. When the oil leakage happens, the alarm buzzes because of the ball, the floating ball comes down and this contact goes up and it makes sorted. Similarly, there are another two contacts we can see here. This is called trip contacts. This in fact it is connected through a vein, okay, vein like structure, and there is a contact which sorts, right. So whenever there is a gas, some gas formed inside the oil because of the interturn faults or because of the local hot spot due to the core in the core or inside the other elements, right. So during that condition, the gas in fact expands the oil, right. As the oil is expanded, there will be flow of oil and in this direction towards the conservator, because this is going to the conservator, and when the oil is flowing towards the conservator, this vein will in fact be forced, right. This is the fixed contact, these two are fixed contacts. Now when the vein will move, then this contact will be in fact sorted, right. This contact will go this side and will be sorted both the contacts of the Buchholz trip circuit, right, and in that way it will trip the circuit. So that means it indicates a fault which is making the local hotspot. So this in fact this alarm indicates a fault which is in fact non-mechanical because of the leakage of the oil, right. So this indicates leakage of oil, and this indicates your local hotspot condition because of the local hotspot because of interturn faults or core interturn faults or heating in core joints, right. So this happens because of this, and in fact nowadays these two contacts are in fact replaced by the mercury switch, and it is advancement we can say, and it is really working very nicely. We can see this here. This is your Buchholz relay chamber, right, and here we can see two mercury switches. One mercury switch is giving in fact signal to the alarm circuit, other mercury switch is giving signal to the trip circuit, right. And we know the mercury is the good conductor of current, so therefore as soon as the mercury level comes here, it in fact what happens, it short circuits these two terminals. Similarly here also, right. So this is floating ball, in fact it goes down when oil leakage level goes down, right. So therefore your mercury level will become in this condition, when it will become flat, your mercury level will short circuit these two contacts, right. So therefore your alarm circuit will be shorted, and hence alarm will be buzzed, showing that there is a leakage of oil. Similarly, when the gas is being formed in the transformer and the oil is expanded, this will go off, right. This hinge will go off. This is a fixed, these are the two fixed hinges, right, hinged points. So now when the hinge will go, this will go up, this lever will go up, and your mercury level will become parallel, and it will short circuit these two terminals, right, and hence your trip circuit will be shorted, and it will give a trip command to the circuit breaker. So this is how it works, right. So this is the another structure of the Buchholz relay using the mercury switches, okay. So this is how it works. Now let us see the analysis of the trapped gases. In fact, when these trapped gases are collected and analyzed in the lab, we can see, we can just find what kind of fault has happened in the transformer. So the trapped gases in the conservator can give valuable clue to the type of damage that takes place inside the transformer. This is because the insulation between the winding turns, the insulation between the stampings, right, of the core and the oil all liberate specific gases when they get heated up due to a fault. So they different kind of fault, like winding turns fault, fault because of the if the insulation breakage happened in the core, or the insulation breakage happened in the oil, they all liberate different kind of specific gases, right. So the presence of these gases can be used as a signature of a particular type of damage that may have taken place inside the transformer. So if we know what kind of gases are being formed, then we can diagnose what kind of fault is happening, where is the insulation breakage in fact happened. So let us consider this table. So here type of gases, if the gases formed is H2 and C2H2, then your diagnosis is arcing in the oil between constructional parts. So the arcing is happening in the oil between different constructional parts. If the gas formed is H2, C2H2 and CH4, then the diagnosis is arcing with some deterioration of phenolic insulation, for example fault in the tap changer, like tap changer, sometimes the insulation breaks in the tap changer. If the type of gas is H2CH4 C2H4, then hotspot in the core joints is happening. If your H2CH4 and CO2 and C3H6, then hotspot in the winding. Okay, so hotspot in the winding happens because of the interturn faults, already we discussed, right? Now we will talk about the phenomenon of overfluxing in the transformer. Already we talked little bit how the overfluxing happens in when we are discussing the inrush current in the transformer. So even sometime under loading condition also the overfluxing phenomena happens in the transformer. How it happens, let us see. Let us consider the basic equation of the transformer, that is V equal to 4.44 phi m Fn, right? Already we know this equation from the basic analysis of the transformer, where V is the RMS value of the voltage, F is the frequency, N is the number of turns in the winding. Thus we can write the flux equation like this. So I can write phi m equal to V by 4.44 Fn, right? So whenever there is an over voltage, frequency remaining constant, the transformer core is subjected to higher flux value. So here from this equation we can see that remaining the frequency, if the frequency remains constant and the voltage increases, then your flux value also increases, right? So in order to support the higher applied voltage, the flux will increase. So by design, power transformers operate at the knee point of the knee of the saturation curve, right? Then I told this under normal voltage condition. In fact, this happens in case of power transformer. Hence, any increase in the applied voltage and the consequent increase in the flux density drives the transformer deeper into saturation. So as the saturation happens, your magnetizing current increases and your inrush current increases very drastically. So the transformer therefore draws an excessive magnetization current. Hence this condition is described as overexcitation. So inrush phenomena happens during the no load condition, in fact, but when we will discuss this overexcitation condition, this in fact happens during the excessive magnetization because of the over voltage. So this considerably increases the core losses, giving rise to overheating of the transformer. Again, it causes overheating of the transformer and it causes the local hotspot as well. Further, saturation of the core causes the flux to flow into adjacent structures, causing high eddy current losses in the core and adjacent conducting material. So this flux, excessive flux, when it is produced in the core, in fact it causes high eddy current loss in the core and also it causes eddy current loss in the adjacent conducting materials. Such an operating condition cannot be allowed to continue for long and the transformer should be tripped if there is a prolonged overexcitation. Okay. So it can be easily seen that overexcitation can also occur in case of low frequency operation of the transformer at the rated voltage. Even sometime your voltage is remaining fixed and your frequency is decreasing for a few minutes, and that also causes the overexcitation. Okay. So therefore these two conditions should be avoided. One is your over voltage and another is your frequency reduction. So let us see the phenomenon of the overfluxing in the transformer. That is, in fact we are discussing this phenomenon of overfluxing in the transformer. So we can see here, if we will plot volts per hours versus time in minutes, then we can see this is your prohibited operating region and this is your operating region, right? This is your operating region. Now we can see that to keep the working flux within the permissible design limit, the V by F ratio must not exceed the permissible limit. Okay, here the permissible limit of the V by F ratio is given, right? So here up to, if we'll increase the V by F ratio, then gradually your operating region is narrowing towards the less time of operation, right? So if it is less, then your operating region will be more, operation will be more for more time, right, more duration. For example, a transformer designed for a per unit voltage limit of 1.25 per unit at rated frequency will experience overfluxing whenever the per unit volt per hertz V by F exceeds 1.25, that is, whenever the voltage exceeds 125% at rated frequency, or the frequency falls below approximately 80%, below approximately 40 hertz or 50 hertz basis at the rated voltage. Okay. So therefore, from this we can find for different operating conditions for V by F ratio, right. Okay. Like here we can see for 125% of V by F ratio, it can operate up to 3 minutes or 5 minutes, right, up to 5 minutes. So thus the overexcitation can be detected by measuring the V by F ratio by a so called volt per hertz relay. So this is called V by F relay, right. So this V by F relay in fact very useful. This in fact works under this principle, this using this characteristic of the V by F ratio and time, right. Okay. So when it is in the prohibited operating region, your V by F lies in the prohibited operating region, your relay trips the circuit breakers. Then let us say the transformer protection application chart. What are the, for what type of fault, what type of protection scheme we should use. So if we will categorize the faults in a transformer, they are of two types. One is internal faults, other one is external faults. So under internal faults, we have phase faults, ground faults, interturn faults, tap changer failure, leakage of oil from tank. These are the internal faults. And in case of under the external fault condition, we have system phase faults, system ground faults, then overloading condition and overfluxing condition. These are the external faults. Now let us see what kind of protection scheme we should use for different types of faults. So protection scheme, here it is given, the primary and backup protection scheme, and this is under this column different types of fault is being considered. So for phase fault, the percentage differential relay is being used, already we discussed, and the backup protection will be overcurrent or distance protection. Similarly, for ground faults, your percentage differential relay will be used as primary protection, and overcurrent and distance relay, they will be used as a backup protection. Similarly, for interturn faults, your Buchholz relay will be used, right, already we discussed, and for oil leakage also Buchholz relay will be useful, and for overloading condition, overcurrent relay with thermal image of the protected unit. Sometimes the thermal image gives the, because of the heating of the elements of the transformer, the thermal image becomes different. So from thermal image also this is protected. Then overfluxing relay, in fact it uses the V by F ratio, and this is called the overfluxing relay, right, or V by F relay. So this is how your transformer is being protected. So up to this we discussed your transformer protection. Now your transformer protection part is over, and from next class onwards we will discuss the bus bar protection, which is also an important topic. Okay. So thank you very much for your kind attention. In the next class we will see the bus bar protection. Thanks a lot.